Alright, welcome everyone to our next video in our series where we talk about everything you need to know for the complex number topic. And today we're going to be talking about operations, adding, subtracting, times and dividing by complex numbers, and also the complex conjugate. Let's dive right in. Right, so the first part is going to be how do we add and subtract complex numbers. We have covered the rectangular form, the polar form, on how to actually get our complex number on a diagram. How do we know what form it is and how do we go in between the forms? But now what do we have if we have two complex numbers and we want to add them together or subtract them? The first rule for today is going to be we only add and subtract in rectangular form. We do not use polar form ever to add and subtract. Let's have a look at how we add and subtract our complex numbers. So here we have a plus bi and x plus yi, two complex numbers that were added. And this is actually very straightforward and easy. We just add the real parts, a plus x, and we add the imaginary parts, b and y, and that's it. Subtraction is the same, then you just do minus instead. So let's have a look at a couple of examples. 5 plus 2i plus 4 minus i. Here the real parts are 5 and 4. Adding them together we get 9. We have 2i and minus I. Together we get 1i. So we're just going to put them together and we get 9 plus I. That doesn't seem too hard. So let's do another example here, just so you're very familiar. What about minus? 4 plus I minus 2 minus I. Well, the first thing at the end, we can distribute the negative and expand the brackets. So we have no more. 4 plus I and then minus 2 and then plus I because the negative and negative makes positive. And now again, we just look for the real part. We look for the imaginary parts and we put them together and we get 2 plus 2i. Awesome. That wasn't too hard. So here's an example that is similar to how a question would look in an exam. You've got given z is minus 3 minus I, w is minus 1 minus 4i. Find z plus w and w minus z. Let's start with z plus w. That's just writing our two complex numbers out, and make sure you are using brackets because z is the whole minus 3 minus 1 and w is minus 1 minus 4i. Well, we have a plus, so we can expand the brackets, nothing changes. And we look for the real parts, minus 3 minus 1 is minus 4. And we look for the imaginary parts, minus I minus 4i is minus 5i. What about w minus z? Give this one a try and see if you get the answer. Hopefully you remember to expand the brackets here, distributing the negative. So then you get minus 1 plus 3 for the real part, and you get minus 4i plus I for the imaginaries. So we're going to get 2 minus 3i. Awesome, that was easy. So we can immediately move on to multiplication. How do we multiply two complex numbers together? Now, here we can actually use the rectangular form or the polar form. You can use both. However, you'll find that the rectangular form can be quite tedious. The polar form on the other side is very easy. Here you have to think, well, what do you want to do? Do you want to transform from rectangular form to polar form, which is quite a few steps, and then do an easy calculation? Or do you want to start with rectangular form and finish in rectangular form? Also, it depends on what the question is asking. If the question is just asking you to multiply them together, you're free to do whatever you want. But the question might ask you, leave your answer in polar form or rectangular form. Whichever one they are telling you, that's probably the one that you should use. Let's have a look on how to multiply complex numbers together in rectangular form. Well, this is actually quite easy. We're just going to be using expanding. You've been doing expanding for many years now, so we're just going to be expanding our brackets using the FOIL method, or whatever you call your method, the claw method. The only thing that we need to remember here is sometimes we multiply terms together that both have an I. So we're going to get an I squared. And remember, we defined I squared to be -1. So I'll put the rule up there. Let's have a look at our first example. Z is 3 plus I, V is -1 minus I, and U is minus I. First, we're going to find Z times V. Well, Z times V, we're just going to leave them in rectangular form, but remember, every time you substitute in, we need brackets around. Here we're going to use the FOIL method, and I've color-coded the top ones and the bottom ones differently so you can make sure you're double-checking where you get to. The only one that is a little bit difficult at the end is the blue part. I times -I becomes -I squared. And remember, we need to substitute in -1 for I squared. So we're going to replace I squared with -1, leaving us with a negative and a -1. So we're going to make this a positive. Putting the real part and the imaginary part together like we've learned before when we're adding will give us -2 minus 4i. Let's do another example. U times V. Well, U times V, we're going to write them out, put brackets around them because we're substituting in for U and V, and then we're going to go through and expand our brackets, and there's only one component in our first one, so we're going to get I plus I squared. Well, I squared was -1, so we replace that with -1. So our answer is just going to be I minus 1. What if we multiply U, V, and Z? Well, if we substitute them in, we can expand all three brackets. But here, and I encourage you to always remember this, you can use information that you've got from previous steps. So in the question before, we found what V times Z was. So that was -2 minus 4i. So we're just going to already find our answer there. Now expanding again, because U is just a single bracket, we're going to get this expression with an I squared. We switch it for a -1 and we write our final answer in rectangular form. Okay, one more. Let's take Z to the power of 3. Well, that means we're going to have 3 plus I times 3 plus I times 3 plus I. And we can just do the normal steps. We can expand brackets just like before. I challenge you to pause here, go through the steps and try and finish this question off. We're going to go through the steps. Here it's important that you simplify first. So put the I and the non-I terms together. And remember, I squared is -1. And now we can simplify another pair of brackets, and replacing the I squared with -1, we get to our final answer, 18 plus 26i. Now this requires a little bit of steps, a few steps, yeah? Making sure that we get negatives correct, making sure that we replace the -1 with the I squared, making sure we put like terms together, the 3i and the 3i in this step. So there's lots of room for error. So make sure that you're expanding these calmly, nicely, one by one. What about Z to the 10? Well, that's 3 plus I times 3 plus I times 3 plus I, and so on 10 times. Feel free to do that as a challenge. If you can expand that, you're going to have no trouble expanding in rectangular form. However, that's going to take a bit of time. And remember, I said that the rectangular form in multiplication can be tedious. So we don't really want to do that. Let's try polar form and see what we can do. If we want to multiply two complex numbers in polar form, we need to know what rule we need to apply. And here at the top, I've written multiplying in polar form means that R1 cis θ1 is our first complex number, and R2 cis θ2 is our second complex number in polar form. Now what we do is we just multiply our moduli together, so the R values, and we add the angles together. You just need to remember how this process works and you'll have no problem. The way that you can remember is that multiply the moduli and add the angles. You'll never forget this now, I won't be able to get that out of your head anymore. But you'll be able to easily answer these questions. So again, we've got three complex numbers here. I don't need to read them out. You can see them. So what is u times v? Well, how do these work? Let's write them out first. We need to multiply the moduli. So 5 times 3 is going to be 15. And we add the angles. And we just use a calculator if we need to. Or you can put them under the same denominator and figure it out. And we have our answer in polar form. Okay, chuck the rule up there and let's do some more practice. What if we wanted to find uz? Pause the video now, apply the rule, and see if you get it right. Okay, we need to multiply the moduli. So 5 times 1 over 5 will be 1. And add the angles. And again, we have a calculator if we need to. We can just chuck that in. What about UVZ? Well, let's write them out. In rectangular form, we had to expand multiple brackets and it was a lot of work. Well, how does multiplication work in polar form? Multiply the moduli and add the angles. Well, we can do that here. The moduli are 5, 3, and 1 over 5. Multiply them all together. The angles are given in blue. Add them all together and we're done in one step. Much nicer. But you need to remember, if they start with rectangular form, you have to first transform them into polar form, and that can be quite a tedious job, especially if you have to find the angle, checking which quadrant you're in. Awesome, at the bottom we've got our final answer. That was quite a neat calculation, very quick and easy. Make sure you know the rule, multiply the moduli, add the angles. Awesome. We talked about a conjugate before in our irrational part, and we needed the conjugate to divide by an irrational number. The concept for complex numbers is very much the same, and I reminded you that you need to know the conjugate concepts for complex numbers as well. So hopefully you haven't forgotten everything about the conjugate in the irrational numbers. We're going to go through what the conjugate is again and how it applies to the conjugate for a complex number. If z is a plus bi, then the conjugate written by z with a bar on top, z bar, or the conjugate of z, is equal to a minus bi. So here we need to change the sign of the imaginary part. So, a few examples. Once we do 2 examples, you'll never forget how to do this. Very easy. Just like irrational numbers. Here's a list of complex numbers. Let's go through them. First one, we switch plus to minus 4 minus I. Second one, we switch the plus to minus 3 minus 2i. Third one, well, we don't have an imaginary part. Imagine this as plus 0i, making minus 0i. Doesn't matter, we just have 4. Minus I, well, we switch the sign for the imaginary part. So we have positive I, and here we switch to negative for the imaginary part, leaving us with minus 4 plus I. Wonderful. And this is the whole concept about conjugates, but they have some special properties. So let's have a look what we actually can see from there. If we use graphing in our arcane diagram, we can actually see what these complex conjugates do in the graph. Here I've got z and z bar, u and u bar, and w bar, or instead of bar, the conjugate of each. I've also got v is equal to the v bar, so the conjugate of v is the same as v itself. Well, here what can we see? We can see that this is just a reflection by the real axis. So the complex conjugate is a reflection by the real axis. And this is why v is the same as its own conjugate, because it lies on the real axis. The imaginary part is 0, so if we negate it, it's still going to be 0. If we're losing a little bit of algebra, then we get z times z bar. Well, what can we have a look? What do we get here? First of all, we note that because it's multiplying, the order doesn't matter. But what happens if we multiply our number with its own conjugate? Here we have our special form. a plus bi and a minus bi, or you can expand one by one, and we're going to find that the middle terms are 0, because remember we have that special expanding formula, and we're going to get I squared is -1, which changes the sign for b squared. So we're going to get a squared plus b squared, and if that sounds a little bit familiar, this is actually the square of our modulus. Because remember, how do we calculate the modulus? It's the square root of the real part squared plus the imaginary part squared. So, with other words, multiplying by the complex conjugate actually removes the imaginary part here. And this is what we're going to be using when we're dividing by a complex number. So, multiplying by its conjugate gives us the real part squared plus the imaginary part squared. And this is the rule that you should know by heart very quickly, because we multiply by the conjugate in basically everything. So, if you are able to go straight to this step without any of these expanding parts, you're going to save yourself some very valuable time for an exam question. If you forget, you can always go back to expanding, figuring out that these cancel out, and you will get to the same answer. So, let's have a look how we divide by a complex number. Let's say we have z as 3 plus I, and we're going to have w as I. What is z divided by w, or z over w? Well, we can just substitute in our values. Then we have 3 plus I over I. Just like the irrational numbers, we don't want square roots in the denominator. Here, we don't want I in the denominator, because we want to be able to split the fraction into real and imaginary part. So how do we get rid of this? Well, remember, we get rid of an I if we multiply by the conjugate. But if we do that in the numerator and the denominator at the same time, we can apply that formula that we've just had in the formula in the slide before. This is very similar to what we've had in our irrational numbers. So let's just jump in and do this. 3 plus I over I multiplied by -I over -I, which is the complex conjugate of the denominator. Well, in the denominator, we know it's just going to be multiplying the conjugates with the original complex number. So it's going to be real part squared plus imaginary part squared. So the real part here is 0, the imaginary part is 1. So we're going to add those together as a square. The top, we still need to expand. It's a little bit of work. And remember, I squared is equal to -1. We can simplify to our answer 1 minus 3i. And we successfully removed I from the denominator. Here's 3 examples of complex numbers. Let's find z over w. And again, make sure you pause the video right now, get your pen and paper, and try this on your own, so you can get the maximum potential learning from this video. All right, hopefully you did try this. So let's have a look. We get 3 plus I over -1 minus I. Now we need to multiply top and bottom by the conjugate of the denominator. So we switch the sign for the imaginary part, copy in the top and the bottom. And for multiplying the denominators together, we know it's the number times its conjugate, so it's going to be real part squared plus imaginary part squared. And here it actually doesn't matter if you use the real and imaginary part from this part or from this part, because this negative here is going to become positive anyway by squaring. So if you take -1 squared from here and +1 squared, you will get the same answer. The top, we still need to expand. You know how to do that by now. Remember, I squared is -1. And then we can simplify. We get -4 plus 2i divided by 2. And again, if you paid good attention in the irrational number parts, this we want to separate so that we have real part and imaginary part. So this is going to be -4 divided by 2 and 2i divided by 2. Well, simplifying our fractions, we get minus 2 plus I. Here's another example, and again, make sure you pause the video right now. I'll see you in a bit. Awesome. Hopefully you tried this one as well. We're going to change the bottom to a plus for the imaginary part, multiply by the top and the bottom. That's your conjugate multiplication part. We remember multiplying by the conjugate in the denominator is a special formula, real part squared plus imaginary part squared. So we just need to expand the numerator. And now again, like in every question, we have an I squared. What does I squared mean? It means -1. Substitute it in, and we get to minus 3 minus 5i divided by 17. If you get to this, well done. Remember, however, we want real part plus imaginary part, so we have to split this. Minus 3 over 17 and minus 5 over 17i. Wonderful. Now, we have done division in rectangular form, which is just multiplying by the conjugate and then putting it in form a plus bi. Let's have a look at polar form, and again you're going to realize if you have a choice, this is the one that you want to use. It is actually basically the same rule as multiplication for polar form, just with a little bit of a difference. Well, in polar form, when we multiply the moduli. Well, here, if we do division, well, we divide the moduli. You can see R1 over R2 is going to be our new modulus. And, well, with multiplication, what did we do? We added the angles. Well, division and multiplication are inverses to each other, so we should do the opposite. Well, that makes sense then that we subtract our angles here. As long as you remember, multiply the moduli and add the angles, you can remember the formula for division because it's just the opposites. Let's apply this rule very quick, nice and easy. We have two complex numbers in polar form. How do we do this? 5 over 10 is going to be our new modulus, and pi over 2 minus pi over 8. Chuck that in the calculator and we get our answer. Next one, k squared cis alpha pi divided by k cubed cis beta. Well, I had to make it a little bit more challenging by removing numbers because this is just such an easy process. Let's try this one. K squared divided by k cubed will give us our new modulus, and alpha pi minus beta is the subtraction part for angles. So simplifying, we get 1 over k cis alpha pi, that is a typo. That should still, of course, be minus beta. There's the same as here. Nothing changes. So I can't cover it, but ignore that positive there. Awesome. And we are at the end of our video showing you how we're going to multiply, divide complex numbers. And I'm not sure what keeps happening with my video at the end, but that's okay. You have heard this before. We are offering all these courses in a nice structured way where you can log in, save your progress, and you can also download flashcards, practice examples of every question, every rule that we have covered in this video. So make sure you check that first link in the description, and I'll see you then. Bye-bye.